You know that flaky, reddish-brown stuff you see everywhere? On your car, on a garden fence, maybe on some old tools in the garage? We call it rust, and it just seems like, things getting old and falling apart. But the truth is, it's way more interesting than that. Because what you're really looking at is an invisible electrical storm happening on a microscopic level. So let's dive in and see what's really going on.
I mean, when you look at a massive structure like this bridge, you're not just seeing decay. You are witnessing the result of a silent, relentless, and incredibly powerful chemical battle. It's a battle that has huge, expensive, and sometimes really dangerous consequences. But how does it all start?
That's right. Every single patch of rust is basically its own tiny short-circuiting battery. It's got a positive terminal, it's got a negative terminal, and it's actively destroying the metal from the inside out. And in this explainer, we're going to make that invisible circuit totally visible.
Okay, so to really get this, we've got to think a bit like electricians, not just chemists. We're looking at something called electrochemical corrosion. And believe it or not, it all kicks off with a simple, spontaneous reaction.
Now that sounds pretty complex, I know, but the basic idea is actually simple. In what scientists call a redox reaction, one part of the metal, we'll call it the anode, gives away its electrons. At the very same time, another part, the cathode, helps oxygen grab those electrons. And what is a transfer of electrons? It's electricity, a tiny, destructive current.
This diagram here is like the blueprint for that little battery. You see, the metal itself acts as the wire, carrying a flow of electrons away from the anode, that's the spot where all the destruction happens, over to the cathode, which is the safe zone. In a way, the metal is literally eating itself alive to power this little circuit.
So, if you remember one thing, remember this. The anode is the active, destructive spot. Think of it as the negative terminal, where the metal dissolves and is lost forever. The cathode, on the other hand, is the safe zone. It's the positive terminal, and while it's essential for the reaction, the metal there stays perfectly fine. This difference is the key to, well, everything. All right, theory's great, but let's actually see this thing in action. We're going to set up a classic showdown, a steel nail versus a copper wire. We'll connect them and put them in salt water. This setup is going to create a supercharged corrosion battery and show us without a doubt who's the bad guy and who's the good guy.
And here's the fundamental rule that decides the winner, or I guess the loser. It's all about a chemical pecking order. When you connect two different metals in an electrolyte, like our salt water, the one that's more chemically reactive, the one that's more eager to give up its electrons, is forced to become the anode. It basically has to sacrifice itself.
So for our experiment, we have our two metals. Steel, which is mostly iron, is way more reactive than copper. We're going to connect them, and then we're going to stick them in salt water, which is a perfect highway for this reaction. So, based on the rule we just learned, our prediction is crystal clear. The steel nail is going to take one for the team. It's going to become the anode and start to corrode to protect that copper.
But how can we actually prove this is happening? We can't see electrons moving around. Well, that's where a really clever chemical tool comes into play, the ferroxyl indicator. It's this special gel that will react to the corrosion process and literally paint us a color-coded map of exactly where the anode and cathode are.
The whole process is pretty simple, actually. You just wrap the copper wire around the steel nail, pop it in a dish, and then pour this special indicator gel right over the top. The gel acts like our salt water, but it also holds these color-changing chemicals in place, so we can see precisely where all the action is going down. Okay, here's the secret sauce. Our gel has two key ingredients. The first one, potassium hexacyanoferrate, turns this deep, dark blue, called Prussian blue. The second, it bumps into any iron ions that are escaping from the anode. The second chemical, phenolphthalein, turns bright pink, where hydroxide ions are forming, which only happens at the cathode. So just remember, blue means corrosion, pink means protection.
And boom, the results are immediate and they're exactly what we predicted. A dark blue cloud erupts around the steel nail, basically screaming, "Hey, I'm the anode, I'm corroding over here." At the same time, the copper wire gets surrounded by this awesome pink glow, showing us it's the protected cathode. We just made that invisible electrical circuit completely visible. How cool is that?
So, now we really get the problem. We've seen with our own eyes how connecting different metals can create a corrosion nightmare. But what if we could take this destructive process and flip it on its head? What if we could turn it into a brilliant solution?
Because this is what happens in the real world all the time. A plumber might connect a steel pipe to a copper pipe, and if they don't insulate it properly, they've accidentally created the exact same destructive battery from our experiment. The more reactive steel pipe becomes the anode. It corrodes away, and eventually you've got leaks and a huge mess.
But here's where the thinking just completely flips. If we know that one metal will always sacrifice itself for another, what if we could choose the victim? What if we could actually control the corrosion and tell it what to attack?
And that is exactly what engineers do. It's genius. Instead of just letting that valuable steel corrode, they attach a block of an even more reactive metal, like zinc. Now, the zinc is forced to be the anode. It becomes the sacrificial metal, slowly corroding away over years, while the important steel structure becomes the protected cathode.
This incredibly powerful idea has a name. It's called cathodic protection. The entire goal is to turn the thing you want to save, a pipeline, a ship's hull, whatever, into the cathode, into that safe zone. And you can do it by attaching these sacrificial metals or even by using a small electrical current to fight back against the natural corrosion circuit.
Now you might be wondering, okay, this is neat science, but why does it matter so much? Well, it matters because of this number, $2.5 trillion. Yeah, that's the estimated cost of corrosion to the global economy every single year. It's an absolutely mind-boggling figure. It represents this constant, relentless war that we are fighting against the basic laws of chemistry. And understanding that tiny little battery on a single nail is how we fight this massive global battle.
So there you have it. From a simple, rusty nail all the way up to a multi-trillion-dollar problem, the science is exactly the same. It's an invisible electrical circuit that we can now see, and more importantly, we can control. The big question is, as our technology gets better and our materials get more advanced, what new, clever ways will we find to win this ongoing war?